Hello dear friends, welcome to this video. This is lecture number 2 on isometries where I would be talking about isometries which are fixing origin. So let's just start with the topic, that is nothing but isometry fixing origin. Let me just give a meaning to it. What is the meaning of isometries? Isometry means a function from Rn to Rn which preserves the distance, that means which preserves the norm, right? The norm of the distance. Norm of x minus y is same as norm of f of x minus f of y for all x and y inside Rn. But when we say isometry fixing origin, that means it will fix, that means it will preserve the origin as well. That means this is a kind of a map which sends 0 to 0. If you remember the previous video, if you haven't checked it yet, I will keep the link in the description. Please go and check. In the previous video, we have discussed three simple example of isometry. One was the identity, right? We were talking about an identity map. We knew that it is an isometry. Can I say this is the isometry fixing origin? Yes, because it will send 0 to 0. So yes, this is an isometry fixing origin. The next we talk was nothing but a negation. Means every vector will go to a negative of it. That means x get maps to minus x. Can you say this is an isometry fixing origin because 0 goes to minus 0, that is 0 for us. So yes, this is also an example of it. But when we say translation, this translation is not an isometry fixing origin because my 0 will get mapped to 0 plus a, where we take a to be some non-zero vector because taking a as a 0 makes us identity. So we think like a is a non-zero vector. In that case, translation is not an isometry fixing origin. Now a question might arise, why we need it? Why we are so much curious about studying the isometry which is fixing origin? Because later on we will find out that given any isometry that would relate to some isometry which is fixing origin and somewhere translation also. So for now, let us just study one of the theorem, or I will say a property of isometry. The property is, if an isometry is fixing origin, then that isometry will preserve the dot product as well. I want to prove this property. Looks difficult, might be simple as well, but I want to make sure that everyone who is watching the video understand. So I just keep some list of pre-requirements. Right? What are the pre-requirement to do those property proof? The first is understanding what is the relation between inner product and norm. The norm x square is same as inner product of x with x. So I can even write like norm of x minus y square is same as inner product of x minus y with x minus y itself. Apart from it, I will be needing some property of a dot product. For an example, this dot product or an inner product, what we say is a linear. What do we mean by linear? By the linear, we try to say that if there is a constant, over here I take this p as a constant, this constant can be taken out. Apart from it, the inner product can be distributed over addition or a subtraction. So what I can write, this is same as p times x inner product with z plus the next part would be y z. What you can do is you can give this p inside and then add it, you can get the what was the initial part. Apart from it, you can even give this p to inside as well, to the second part as well. Since we are working on the real inner product, we are not worried about what is the first coordinate, what is the second coordinate and the inner product, because in the inner product, your inner product of xy and yx is same. But this works only in the case of real inner product. Okay, if you are working on the complex inner product, the scenario will change. That becomes a conjugate of it when you switch the position of it, right? Then it becomes conjugate if you are working in complex inner product. But for the real, it is much simple, right? So these are the simple basic property which would be required to me. So what is there in my mind? I want to prove that isometry fixing origin, that means preserving origin, will preserve the dot product as well. Before I start the proof of that property, let me just make one good observation. So suppose if I want to start with this norm of x minus y the whole square, what I can write on this place? I can write this is same as inner product of x minus y with x minus y. Right? This is something that we have learned in pre-requirement. And this can be written as what? As we have learned the inner product is linear, I can distribute this x to both of them inside inner product. Right? So once I distribute this, it becomes x with x. And then there is a minus sign, so I'll write minus sign x with y. Right? Then what I do? Then I distribute this y to everyone. So this y goes with this, and then y goes with y. So that y goes with the minus sign. This is nothing but yx, and that minus minus will become plus to me in a product of y with y. Right? So now we know inner product of x is same as what? That is same as norm of x square minus inner product of xy as it is. What we have learned for real, writing interchanging this two will not affect the answer. So I will just interchange it because I have something similar. So that becomes okay. This inner product of y can be written as what? That can be written as a norm of y the whole square. What will be the next step? Next step is nothing but writing this is same as norm of x square plus norm of y square minus 2 times inner product of x and y. So this is one of the result that you can use directly from now whenever it is required. But this is true for real only. That means when you work on a real inner product, in that case it is true. Right? Because I have used the property of being real in this case, right? To interchange, I am using the property of real. So this result is true for real. So with this observation, with this result in the mind, let me just start working on the proof of this. My isometry fixing origin, if and only if it preserves the dot product. So first of all, let me just write what I have observed. So I'll just write for the proof of this. For the proof of this, I'll start from, we know that my norm of x minus y the whole square can be written as norm of x square plus norm of y square minus 2 times inner product of xy. And similarly, I can even write the same thing for what? I can even write the same thing for f of x minus f of y. Correct? So that is same as what? That is same as a norm of f of x the whole square plus norm of f of y the whole square minus 2 times inner product of f of x comma f of y. So this is something that we know from our observation. Now let me just start the proof of this. This is something that we knew. Now it is if and only if, right? So if and only if, that means you have to prove this result in both the direction. So suppose I first assume, suppose my f is isometry fixing origin. So if it is an isometry fixing origin, isometry means what? We know that my x minus y is same as, norm of this is same as norm of f of x minus f of y. Right? And this is true for what? This is true for all x and y inside your Rn. What I do, since it is true for all, I just take my y equal to 0. So what is my f of y? Can you tell me what should be my f of y? If there were some student, I would have asked. But for now, I have to answer this question. my f of y is going to be what? It's going to be 0. Why? Because we know that my this isometry is nothing but fixing origin. If it is fixing origin, then my f of y will be 0 since my y equal to 0. And so f of 0 must be 0. So if I use that property, what I find is I can see that my norm of x is same as norm of f of x, and this is true for all x inside Rn. So there is one more thing that you are learning over here is if it is an isometry fixing origin, it will preserve norm. Norm by the definition only. But what we want to prove? We want to prove something more. We want to prove that it preserves the dot product also. Right? Okay. So we want to prove that it preserves dot product. From now I know this is norm of x is same as norm of f of x for all x inside Rn. So what I do is for x minus y inside Rn, since I know it will preserve the norm, so I can write norm of x minus y would be same as norm of f of x minus okay okay, I think we cannot directly use it. Norm of f of y. Can I write it like this? Okay, I can write it like this. There is no issue in it because we know what we are using, right? Okay, this is fine. What should be my next step after this? Right? What should be my next step? Okay, we directly knew this, right? Since it is an isometry, we don't need this. We don't need this x minus y, right? We know that for x comma y, yes, this is fine. For x comma y inside Rn, this is true since f is isometry. So if this norm is true, we can even do square of it. It would be same. Why I am doing the square? Can you see on the screen? Can I see from 1, if I give it a name, and 1 and 2, what I can see is this 1 and 2 are equal now for me. If these two are equal, then we know that this norm of x the whole square plus norm of y the whole square minus 2 times inner product xy would be same as norm of f of x the whole square plus norm of f of y the whole square minus 2 times inner product of f of x comma f of y. Is it fine? And from this result 3, what we have found that the norm would be preserved. So norm of x would be same as norm of f of x. Can I say the norm of x square would be same as norm of f of x the whole square for all x inside Rn? This would be true. If the numbers are equal, the squares are also equal. The reverse way is not true, by the way. Correct. So based on this, what I can do is, I can see this is equal to this, so I can cancel. Similarly, this is equal to this, so I can cancel. So what I'm left is, I'm left with this part is equal to minus 2 inner product of f of x with f of y. Now what we can do in the next step is, we can even cancel this, which implies that what we can say is, this f has preserved the inner product, right? We can see what it is doing is, my inner product of xy is same as inner product of f of x f of y. So what does it mean? This means that it is preserving inner product. Okay, so in this slide we have proved that if it is an isometry fixing origin, it will preserve the inner product, right? In the next slide, what I want to prove is, I want to prove that if I have an isometry which is preserving inner product, then my isometry will fix origin also. So this is nothing but something that you are supposed to think, right? That is nothing but the converse part of this theorem, right? Try to do it. I will upload the proof of this in the next video, so stay tuned to this channel. If you have any doubt, difficulty, be free to ask in the comment section. I hope you like this video. If there is anything that you feel, you can give me a suggestion in the comment section. Okay, bye bye.